have one of these beloved PowerPoint things here. I swore way back that I would never do it. Over to the dark side. Let's see. Can I kill Goddard here?
Yep.
So, based on the title and the other participants, and Seth was going to be here, and Dan and so on, I decided that probably I should talk about other than radio. But I don't want to give the impression that radio isn't catching me out, but it really is. So let me just say a few things here. Just click on that little hourglass. Where is it?
Down at the bottom.
Oh yeah, that guy. It always looks like a wine glass to me. Why is that? This came from Ed Purcell's 1960 talk at Brookhaven. A really marvelous thing if you guys haven't read it. I think it's reprinted in the Goldsmith collection. It's called Radio Astronomy, Space Travel, or Radio Astronomy and Communication Through Space, I believe. It was for a general scientific audience, so he has graphs like this. I like this because, you know where we're looking? We're looking in those two holes because it's easy. And because in 1960, you really couldn't imagine doing much of anything else. The first satellites were going up, and we didn't have no space on them for SETI, even now. So the optical window and the radio window, the radio window, of course, contains the 21 centimeter line. And let me make a comment about radio before we move on to optical, which is that I've heard at this conference people bemoaning the fact that Earth is becoming radio quiet. And that if we're becoming quiet, so are they, and we're never going to see them. And it seems to me that I find this completely unpersuasive because we're not looking for leakage radiation anyway. We never said we were. The numbers are kind of outrageous in huge flight-free areas. And if they're doing their job well, these signals aren't going to be particularly detectable. That's the lost radiation. We're looking for a deliberate beacon, and those are the calculations, the megawatt, 600-foot dish, and so on, with the days of Ozma, considerably better now. And if it's a deliberate beacon, it doesn't have anything to do with how they do their cell phones and their fibers. It's a completely separate thing they do to establish a channel, bring folks like us in. And in fact, it's the other way around. If they're not radio noisy, the radio detection is better. I mean, what we hate is RFI. So I'd say that the Earth becoming radio quiet is good news for SETI. Have I missed something? All right, anyway. The arrow here. So you all know this stuff, and Tony Morrison sort of simultaneous with Drake, saying that microwaves probably a good place to go, electromagnetics in any case, and 1420 megahertz, megacycles per second. Let me just show you a little historical picture. This is the dish before it arrived here, and that's Doc Ewan on it, sort of a contraption put together, really based on wartime microwave technology that Purcell and others have been doing just down the river at MIT in the MIT Rad Lab project. That's Doc Ewan up there. And what's close to Doc Ewan's right hand? A patch. I guess they just got some copper foil from the shop. It had a hole in it, so they had to patch it in. Now, I went looking for that patch, and it ain't there. So some of you historians of science out there, you know who you are revising history. I think we should put the patch back. So you're in sharp play. Anyway, there it is. And at the other side of the, this is the other end. There's the horn, the feed coming down in. That's basically 21 centimeter waveguide. And here's the receiver, circa 1951, when this was done. It used some more surplus stuff. They used the communications receivers, the IF. There's a Simpson VOM hanging there. Any of you guys seen that? If you're not an old-time nerd, right? And look what's hanging on the right-hand side of the rack, 2/3 the way up. So there's the earphones that was missing. Right. And this was an inexpensive experiment by today's standards, even by then standards. Here's the last piece of the proposal that Ed wrote to try to get a little bit of money out of one of the private funds at Harvard. And he says, you look at this thing, and defray, I request a grant in the amount of, here we go, $500. That's one of the least expensive discoveries, I think, in radio astronomy. Okay, so, now optical sort of does some of the same kind of calculations as radio. I'll zip through this at warp speed. This slide was generated for a not too technical audience, but, can you communicate over these distances? Well, let's do a little calculation here, and there's your little nerd box with calculations. $1 worth of radio transmission results in a pretty small amount of power received. Here's a little cartoon about But that's not very much energy. It's a trillionth the amount of falling snowflake, but it has to compete with thermal noise. And thermal noise is way down, so the received signal is something like 10,000 times noise. So you transmit a dollar's worth of radio power, and this is kind of a 1960s type. Well, these are RCBOs, I guess. 300-meter dishes, 1,000 light years apart. 1,000 light years, a good chunk of the interesting piece of the galaxy. Got about 1 million sun-like stars there, and you transmit a dollar's worth, and it's 10,000 times noise. You can send quite a message there. In other words, this is sort of taken from Ed Purcell's talk back there in 1916. Interstellar telegrams are cheap, and that was sort of the basis of saying radio waves really are a good way to do it. They're much better than gamma rays that come to Mars and stuff. And this was 1959, 1960. Here's 1961, a year L+1, the year after lasers were demonstrated, where Schwartz and Towns are pointing out that it's not so obvious that these newfangled laser things won't actually be pretty good for this kind of stuff too. And here's a little piece of the abstract where from Charlie Towns' 1983 paper, where he says that we've all been following the microwaves because it is an awfully good way to do it, but really you should look and see. Take a look at our lasers here, they're pretty cool, and if you don't do coherent detection but do photon detection, it's actually pretty good. The short wavelength and high directivity of apertures makes up to a large degree for the higher energy in photons, and in fact if you take the whole system calculation, it's not all obvious, it's not better way to do it, certainly in the running. By the way, you'll notice down at the bottom it says here, the publication costs of this article were defrayed in part by page charge payment. This article must therefore be hereby marked advertisement in accordance with, and there's some US statute here, that at least one person in this room is probably familiar with, that says that you have to do that to indicate this fact. So here's Charlie's ad for optical SETI. Here's Frank Drake on the 84-foot telescope at Harvard, deciding that maybe optical is actually the thing to do even if you do it from radio telescopes. This telescope was, 84-foot dish was put on top of what used to be a 60-foot dish, and I actually have right here, the actual guest book sign-in from 1956 when this 60-foot telescope was put up at Harvard. Yellowed pages, falling apart in the binder. I'll just show you the one interesting page here. Well, two-page spread here. Here's Frank on the right, 3 down. He's below Roger Hickman, the inventor of the regulated power supply, probably a name you're not familiar with. But over on the left, there's Ed Purcell. There's the Gaposhkins. Let's see, there was another. Shapley, yeah, good company there. It's about page 10 of this thing. Anyway, I have it here. You guys can page through it, try to find your names here if you like. And I was told by Frank and by Peter Gallison the other day that in fact it was this telescope that the idea for Ozma really got born. And Frank can confirm this, that he was looking at hydrogen in the Pleiades, and there were 2 lines, the Pleiades Doppler shifted and also the background galaxy, and at one moment a big spike pops up in the middle, right in the middle there on the Pleiades cluster wavelength. It wasn't the real thing, but it was said, wow. All right, let's see. So over to optical. Here's the sort of optical counterpart, and that's really just, we'll talk a little bit about this because this is what we're doing. I think I've overrun my 5-slide limit, but really zip through these things fast. The idea is that a state-of-the-art laser really puts out quite a strong signal if you shine it off of something like a Keck telescope. Here's the early stuff. This is, I guess, a Himi laser. But here's the idea of what you might be able to do. The current incarnation of this would be NIF with their very powerful lasers, a petawatt type power. This is actually designed for a fusion, a laser pumped fusion plant. It's a very organic and green plant. You'll notice that there's no garbage cans or anything. There are some power lines connected to it, but those power lines are doing the right thing. Power is going out of this plant. You can see the pointing vector just going that way. Yeah, that's the concept. Fusion has always been 30 years away and always will be, I guess. But here's sort of the history of lasers. Those red dots are the power of lasers on a pretty logarithmic axis there. It's in units of terawatts, so it goes up to a petawatt there. And you'll see that in the mid-90s there, basically they went over a petawatt with the neodymium glass laser at, I guess that's at Livermore. This is quite a lot of power. You can see that little dashed line, that actually dashed blue line there represents the total electric power output of Earth. 3 orders of magnitude down from what a laser can do during one of these pulses. That little dip there, by the way, you can tell this is real data, because that real dip at about 2001, that was the California blackout power. You guys in California know what went on there. Enron guys were screwing you. Anyway, I actually only used 2 data points to get the dashed line, because I had one around 1950 and one around 2000, but the straight line is pretty good, don't you think? Anyway, let's see. So optical looks pretty good. Oh, there must be some more things here. Here's the nerd box if you want to check the calculations here. But basically a pair of kecks 1,000 light years away, and you fire one of these pulses, and you get about 10 to the 4th photons at the other end. Or, I'm sorry, you're about 10 to the 4th times brighter than the sun, and you get about 1,000 photons of the pulse through the aperture. So it's plausible. It's certainly something you can do. Oh, there's a little zoom key there. And, you know, for directed communication rather than beacon, you get a lot of gain. You get 150 dB gain in a keck compared with 70 dB gain in an RC-bone. And that makes up for a lot of other things. The interstellar medium is undispersive at these wavelengths, largely. There's a little bit of scattering. A little more on that later. Lasers are getting much more powerful, much more rapidly than radio transmitters, which sort of makes up for the head start that radio had in 1960, and so on. Oh, there's that and that again. So we put together this little experiment, and I don't want to talk too much about our particular stuff, but we got all excited about this when I think it was SETI 2020, but the SETI Institute had a conference, and Charlie Towns gave a great talk explaining that we should have been listening to him for the last 20 years, and this is good stuff to do. So we corralled the 61-inch telescope. Does that look like a telescope? We sort of believe in tradition at Harvard. Anyway, we took this thing which was doing which is around Latham and Stefanik were doing a survey to look for stars without binary companions. I think in support of the SETI Institute and NASA work at the time. And we put a beam splitter in there and grabbed half the photons and put it onto a detector. And we got Princeton involved in this at the same time, Dave Wilkinson, and they're 36-inch, I think. And we did simultaneous observations, which is a really good way to deal with the single events. I mean, what else are you going to do when you have one pulse? And we heard earlier in this conference it might be 1 pulse per year that they send. And that's really discouraging if you only have 1 aperture. So we had these 2 apertures, and we were synchronizing things through the internet. And the nice thing about these is they're definitely in a different local environment. But furthermore, the light travel time between them is a few milliseconds. So you can disambiguate. If something comes and you think it's come from where your telescope's pointed, it better have come at a different time at the other one. And that provides really a pretty tight constraint. It limits you to about 10 arc seconds or 20 arc seconds on the sky because of that baseline. Okay, anyway, just zipping along. So there's the Wilkinson and Company setup. Here's some other guys doing optical study, maybe some recognizable folks there. That grouchy looking guy in the lower left corner doing a 3 photomultiplier detector system. We've been working more recently. We built ourselves our own little telescope here. The 61-inch finally shut down, so we built a 72-inch transit telescope with a roll-off roof. There it is. There's Andrew Howard sitting there doing something. What's that? Oh, just another picture of it. There's a few more of our guys doing this. This is really sort of a small, homegrown university-type operation here. There's Andrew Howard and Curtis Weed. And so we're now running this thing, that was the progress in covering the sky. About 1 month into it, I see you looking at your watch. I'm zipping through here, warp speed. We've now covered the entire sky visible from the north at least 3 times with coverage and double coverage in many places. This thing automatically goes back and looks again if it sees something on the next night. It actually goes back and looks immediately because we have a staggered set of detectors, so you can actually tip up and let the thing run through the next detector and see if you've got anything. I guess I'd say, and maybe this is the more interesting intellectual content, why are we doing visible anyway? Just because that's what comes through the atmosphere. But it's really the wrong place to be. It comes through the atmosphere and the detectors are good because you have an electron volt and it's easy to kick an electron out of a photomultiplier. But it's the wrong place because of opacity of the galaxy. Really, you know, you go out to 1,000 light years and you're already getting some significant extinction. There it is, a couple magnitudes per kiloparsec. And of course, you can't see anywhere into the galactic plane any reasonable distance. But if you go out to a few microns, you do pretty well. And there's a little picture out of Allen astrophysical quantity. Furthermore, if you go to the infrared, the photons are cheaper, so you get more of them per erg. And stars get dimmer because you're sort of on the backside of the black body spectrum. So we really should all be pushing into the infrared somewhere between a micron and 10 microns, depending. And the trouble is it's just really hard to do. So that's what we're doing wrong, and that's why we haven't found these guys. I just sort of finish again with this picture of, this is a different view, but of the same thing that Ed Purcell had rather sketched more simply, which is, we're looking in the holes there, we're looking under the street lamp, but we're really making a mistake. And I think one can make similar arguments about short wavelength radio, that perhaps we should be pushing up to shorter wavelengths. The atmosphere is a kind of annoyance there, and the technology is more difficult, but there's less dispersion in the galaxy, there's more directivity of antennas. There's some nice reasons to do it. That's the end of the real slides, and I just have 4 slides here showing a little bit of historical thing. We name our computers after SETI people. We have a Dan, we have a Jill, we have a Barney, and we have a Frank. And this is Frank. Frank is actually our server. And this is Frank meeting Frank. And asked to autograph it, so here. And then, of course, you have to sign an autograph. And Frank was quite bemused. I've been asked to autograph a computer.
Well, thanks, Paul. We should have maybe just one question for Paul, and then we can come back to questions and comments for Paul, because I'd like to finish up, and then we can all talk about everything, if you don't mind. Any questions or comments? Yeah, Joe.
I guess just real quick, I was going to ask the question about interstellar absorption. Have you got some map or some view of exactly how far out you probe for various energy pulse?
Well, in the radio, of course, it's transparent. We do well,
yeah, I was thinking
except for dispersion, and we try to match our bandwidth to that, so we're doing pretty well, except in the most dense regions where it's dispersed. And it's not pulse dispersion in the radio; it's spreading, and you know about that. You're the guy who does that. In the visible, basically, we figure that we're probably going out to something like the thickness of the galaxy in our region. So we're looking probably out to 1,000 light years. We're probably capturing something like 1 million sun-like stars, except we're only seeing about 65 or 70% of the sky because we're stuck, we don't see the south. But, according to you guys' calculations, we're doing okay with time resolution of order 1 or 1.5 nanoseconds, which is what we're doing with PATs. And we're looking, by the way, I guess I didn't say it, but we use a beam splitter and everything is replicated. We have to have a coincidence before we consider that a pulse.
Jacob, do you mind? I just want to hold. I want to make sure I get through everything, and then we can come back to Paul. Okay. Okay. So I want to talk a little bit about what we're doing at Berkeley. There's about 18 people at Berkeley, and we're also working with Frank and with Rem Stone at Santa Cruz and Jim Cordes at Laura at Cornell. And we have a lot of different programs. We have several radio programs looking for sort of narrowband signals, pulse signals, Arecibo, a little bit on the ATA. We have some visible programs that Paul talked about, some looking for pulses, some looking for narrowband in the visible. Paul showed this slide of the thing at Lick Observatory. And Jeff Marcy's doing a search at Keck looking for narrowband signals with high-resolution spectroscopy. This is one of our early searches here at Green Bank using this 300-foot telescope. And while we were using it, this is what happened to it. And you might ask, how did that happen? And the answer is the aliens did not want us to discover them, and they zapped the telescope. And so we're testing that zap theory, and I was, there's another telescope we use where the ATA is now in Northern California, and that's what happened to that telescope. So anyway, I was driving along, and I was thinking about where should we test this zap theory, where should we go next? And I saw this advertisement on this U-Haul truck, and it has this nice telescope here, and the Drake equation, which is hard to see there. And I said, oh, we should go test the zap theory at the GBT. And so we've been talking to people here this week about doing some SETI here. Mostly we're testing the zap theory at this telescope, and we have this multi-beam receiver, and there are a lot of people surveying the sky at Arecibo, doing pulsar work, extragalactic work, galactic mapping, and pulsar work, and we're also surveying the sky with them, doing several SETI searches. And some of our searches analyze the data in real time with hardware at the telescope, but also we're storing this data. And Jay, you were asking about that. We could go back and look, and we found supernova remnants and sheets and filaments and stuff with that data. A lot of people use that data and, that we've stored, and we've gone back and looked through it in different ways for SETI. And one of the main ways we go back through it and look was this SETI home screensaver. It's allowed us to do a very sensitive search, about 10 times more sensitive, because it has a huge amount of computing power. It's the third largest supercomputer on the planet. And we've been able to do this coherent detection that is, you can't really do that unless you have a huge supercomputer. That makes it very sensitive. And also it allows us to look for a very rich variety of signals. And that led to a whole bunch of different computing projects that use our software to do global warming research and HIV, malaria drugs, and a bunch of things. And now there's a bunch of ways you can do participation. This is a project, by the way, that Woody Sullivan started with us a little more over 10 years ago that led to all this distributed computing. And the Gravity Wave project, Einstein at Home, just found some new interesting pulsars that are quite spectacular, protein folding. And that led to this citizen science projects where instead of just using your computers at home, using your brains and your eyes. An early project that we did was the Stardust at Home project, looking for these little particles of dust, where we had about 100,000 volunteers looking for these little particles. And there are a bunch of people that use our software or have developed their own software. There's the Stardust thing. And the other thing we're doing is we're trying to figure out how to build instruments very quickly and inexpensively. These huge SETI machines sometimes take many years to develop, and we have a big collaboration trying to figure out how to develop not just SETI instruments, but pulsar instruments and spectral imaging instruments, VLBI instruments, and there's a lot of people working on this together. And it's now, these instruments are being used at a lot of different observatories, including here, the pulsar instrument looking for gravity waves here, and the reionization, the reason that you couldn't take pictures yesterday when you were climbing on the telescope, looking for when the very first stars and galaxies formed, is using some of this instrumentation that came out of our SETI work. The thing I'm most interested in is lately are these the pulse searches that Jay was asking about. And Andrew Simeon led this pulse search on the Allen Telescope Array. And recently Josh Von Kort just finished his thesis doing a search at Arecibo. And these are looking for pulses that are dispersed. So as a pulse travels through the interstellar medium, the low frequencies get delayed more than the high frequencies. And you get this kind of chirping thing. And it turns out if you want to look for very short pulses, you need a huge supercomputer. And we just happen to have one of the biggest supercomputers on the planet. And we can do this coherent integration, look for microsecond pulses. And this is what we found at Arecibo. We found about 100 interesting candidates and a lot of them are concentrated in the galactic plane. We don't know what these things are. Could be ET, I sort of doubt it. Could be interference. Could be primordial black holes. Could be these things called R-rats, which are pulsars that go on for a little while and then go off for a long time. Anyway, we're going to be following up on those. The Arecibo just granted us a bunch of telescope time to try to figure out what these things are. So I think that's it. And I think now we should open it up for questions